My name is Boris Fain. I come from an academic background a long time ago, but I haven't been in academia for quite some time. So I work with a bunch of really cool people in a startup, and the goal of our team is actually to make, what people always said to do is to make simulation be simulation be a real part of the scientific process, molecular simulation, right? So the promise has always been that everything will be done on the computer and experiment at the same time, but anything from wind tunnels to to reactions and everything, but that hasn't really been the case. I have to say, since molecules were first on the computer in the 60s, right? If you take something like just taking sugar and putting it in a cup of coffee, right? And you ask yourself, what is the free energy of that reaction? I just want to say, people poo-poo salvation, but a lot of people here are physicists, almost everyone. So if you know the free energy of something, you pretty much can get everything about that system, right? And so the answer, state-of-the-art answer for just putting sugar in coffee is something like minus 18. And experimental answer, and the experimental answer is minus 25. So minus 18 is your state-of-the-art prediction for, I guess, we have Peter Coleman's former students here, so Amber. And that's just not the kind of accuracy that you could actually do anything with when you want to predict things for real, right? This is a little self-advertising from Schrodinger, right? So when you put 5 or 6 systems in a sausage, it does look like a straight line, but actually if you look at every single system, it's basically a circle, right? So no single system can predict ligand binding, but of course, since they're vastly different energy scales, you can put them together on one line, make it look pretty good. This isn't something we made up, this is their own advertising, right? So quite some time ago now, Mike Levitt actually came to us and said, hey, it's complete academic suicide to start to form intermolecular models from scratch, right? You can't publish for 5-6 years, right? You'll get absolutely no credit. It takes a lot of money. Why don't you guys go try it outside of academia? Let's see if that works out, right? And that's what we started to do. And so there's an article by Professor Hug from UCLA that says, there are some holy grails of computational chemistry. A few of them have to do with DFT and things like that, but the ones that are basically the big goals are accurate polarizable force fields, accurate protein ligand binding prediction, and accurate salvation energies. I would not put them in that order. And he predicts, this is a couple of years ago, that these things will be actually solved from 2040 to 2070. This is not inaccurate, this is not, he just puts a finger somewhere in the future, not the really far future, but really not 10 years from now, right? This is something we should get. We should be able to do these things computationally, and we can't, all right? And so I guess I'm here to tell you that the wonderful group of people I work with figured that out now. And there is really no magic. It's not, we're not inventing quantum mechanics or general theory of relativity or string theory, right? So someone should be able to create a Newtonian Hamiltonian or energy of a system that corresponds very closely to that of a quantum mechanical energy of that system. That is the prescription, right? It's not a mystery, right? It's just really hard to do. And another thing that is not really clear, right, is what does it mean exactly? How precise do you have to get that, to make it be useful? Well, it turns out, and this was a surprise to me, right? So biology is one of the most flimsy and difficult things to model, right? Because if we were a rock, it would be easy. But the reason we breathe, the reason we think, the reason we can, move around, the reason an egg is like this at, 50 Celsius, but something a little different at 75, is because that richness is accomplished by really big numbers barely offsetting each other. Okay, so this is a little diagram I want to tell you. What I'm trying to say here is that it's really difficult to model biology. So this is a diagram of typical processes that we care about. So on the very top is, let's say let's call it hydration or solvation. So 2/3 of biology takes place in water, right? We're not in water, but we carry water, in us, right, to preserve that. And the things you care about, like a benzene atom dissolving in water is maybe -5. So that's a bunch of numbers that are a little bit bigger than that, plus or minus, you add it together. When you go into batteries or ionic mixtures, it's kind of the same thing, but every number is 10 times bigger. But if you look on the bottom, let's say you put a ligand and a protein into a protein, right? You have ionic interactions. You have literally dozens of interactions on the strength of 15 and 20 kilocalories per mole, and your medicinal chemist will not actually even try something new until you give him or her an accuracy of plus or minus 1. This is a really difficult challenge, and something I did not actually anticipate, right? There's another sort of, because proteins are liquid crystals, there's another challenge here, but I'm not going to go through that. So there have been a really beautiful explosion of models in the last 2 years that are derived from first principles, from quantum mechanical calculations. That is absolutely the way to do it. There is not anywhere close to enough training data from experiments to make anything empirical, right? And quantum mechanics gives you the training sets. But the workhorses of molecular dynamics are, as you can say, AMBER, OPLS maybe. These are models from the 60s and 70s, and they haven't changed that much. So the first thing we thought we would do, and that, there are reasons for this, is we thought we would try to make a polarizable force field from first principles. I mean, it's not an easy thing to do. I just want to impress upon everyone that this is maybe 1/10 of the formulas we used. We used a gigantic amount of formulas. Formulas are complicated, right? And we wanted to make sure that we made something that reflected polarization correctly for a reason. And we did do that. We managed to do that. The reason to do that, one of the reasons to do that, is because the data you need to make a model for bulk for various systems can come from dimers if you do it right. It's a bit intricate, but if you do it right, you just need to compute pairs of things. And in chemical space, for example, to go into triples would be a humongous punishment, right? Because you need triples of everything to everything. So dimers are the big deal, probably cannot go beyond that. And so, we did, we danced around very happily, and we dissolved things in things. We dissolved all conceivable neutral compounds in water and in cyclohexane and in hexanol and so on and so on, and we got that right. So I started out with a slide that says you should be able to put sugar in your coffee without having to do an experiment or doing something like sugar and something like coffee and actually predict what happens. And so we did that, and that was really satisfying. That work was actually finished in 2018, I think. And then, of course, the next thing to do, and the juicy thing to do, is to go into a protein system. I don't want to say that accurate. Go ahead. Sorry, almost done. Okay, 1 minute. Okay. So I don't want to say that accuracy is the only thing. Sampling is a big deal. But we didn't actually succeed. It was a spectacular failure. And so recently we found out that some of these newfangled machine learning methods could be a real help. And the trick was to combine them with formulas in a way that actually gives you the accurate prediction. And now, actually, we have achieved the goals that I set out, in the beginning. So we can dissolve salt in water, right? We can get the answer to within 2% from first principles, only quantum mechanics, no fitting to experiment. We can actually determine the pH of water, it's a recent experiment, to within kilocal, right? Which is, a 1% accuracy. And of course, when we do ligand binding experiments, finally, they are correct like they should be within, to chemical accuracy, right? And that, I think, pretty much is the talk. Okay, thank you very much. Yeah. Okay. Yeah.
Great, replacing quantum mechanics.
Yeah.
Great talk. Can we dissolve cofactors in proteins?
Yeah, I mean, we just enabled this thing, right? And there is quite a bit of, there's a price to pay for hashing up quantum mechanics, right? This is what we're doing effectively, right? We're not inventing something new. We're hashing up QM, right, in a clever way, right, economical way. So there's a price to pay for that. You have to do a lot of quantum mechanics once, never again. So you can see yourself, there's quite a bit to be done to do those larger things. Once you do that, store it properly, put it in the model, forever after, you can do those things.
Yeah, the reason I asked was because you have Marcus theory there waiting for you. essentially
We've done, yeah, Markowitz theory is really ugly.
Yeah,
Right.
the rate of electron transfer
Right.
will be, is dependent on this polarizability, which no
Right.
proper force field can do now.
No, I mean, literally like 2 days of couple cluster and a little bit of putting stuff together and you have the pH of water. Imagine doing that with a Marcus model with 15 boundaries and approximations. Right, exactly right.
Yeah,
Yes.
so I want to understand what's different about your model than, let's say, MB pole. So, a lot of
So-
people have been working on similar cluster kind of
MB
expansions.
Pole's been around for what, 12 or 15 years or so, right? It hasn't gone beyond water and maybe an ion. There's a reason for that, right? And the reason is, there are two reasons for that, right? So unfortunately, MB Pole started before GPUs and AI. If they had known that, I'm sure they wouldn't have gone in that direction, right? It's incredibly slow. But the real reason MB Pole is a dead end is because it relies on ultra precise things, which you kind of have to know how precise you're going to be places, right? And MB-Pole relies very heavily on triplets and quadruplets. That does not in all generalize to chemical space. It's not tractable, right? You see what I'm saying, right? Yeah.
Okay, and
Yeah.
our question is, which architectures is this relevant for?
So there's a bridge there, and like there are laws of physics that show you how the beams are done, right? So we want to provide for everyone the underlying rules of how these things behave and assemble. So hopefully, in 5 years or so, you can actually do a lot of your work on the computer and believe it. Okay, like that's it. Yeah.
Okay, wonderful. Thank you so much.
There's
Okay, let's take one final question and then.
I was just curious to, maybe I missed it, but what kind of data do you use to train?
Quantum mechanics, dimer calculations, sometimes trimer just to check.
That's synthetic data that you,
Say it again.
is it synthetic data you use to train? Or? Is this synthetic data or is it?
In like not simplifying it too much, you take two, I don't know, dimers. You take a dimer and you compute its quantum kinetic energy and maybe some components, and that's it. Right? Yeah.
Awesome.
Yep.
Thank you
Thank
so
you.
much.
Great questions too. Thank you very much. Yeah.